Hi everyone, in this video we will learn about the kappa nearest neighbor algorithm. This is one of the simplest and most intuitive machine learning algorithms, and in particular it belongs to the category of non-parametric and lazy algorithms. Okay, but the core idea, to explain the core idea, I put in this part this phrase: tell me who you work with and I'll tell you who you are. And so how does it work? Given a new point to classify, the KNN algorithm in a first part calculates the distance between the new point and all the points in the training set. And in the second part, it selects the kappa closest points to the new point, and in the last part it assigns the majority class among those kappa neighbors for classification, but it can also be used for regression problems. Okay. The baseline of the kappa nearest neighbor algorithm is the function of distance. In particular, the most famous one is the Euclidean distance. If you are talking about and seeing the points in a geometric way, but in a real manner or in a geometric way. But other distances can be the Manhattan distance, the Minkowski one, or the cosine distance. The kappa parameter is important because we can choose it based on our problem. In particular, if kappa is small, for example 1, but 1 is a particular case, we have high variance and zero bias in case of 1, and in general high variance and low bias. Instead, if we choose a large K, for example 50, we have low variance and high bias. So we have overfitting in the first case and underfitting in the second case. In the first case we have irregular decision boundaries, and in the second one we have smooth boundaries. Another special case is K equal to the dataset size, and so we have that the algorithm predicts only the most present label in the training set. The optimal choice of K is typically found through cross-validation. This is the algorithm step by step, but we already say that. The advantages are, for example, very simple to understand multi-class algorithm, good with nonlinear data, but it suffers from the course of dimensionality. It requires a lot of memory because this algorithm is lazy, and so it only saves all the dataset and doesn't perform a real function to predict the test set. And an important thing to remember is that we have to normalize the data before implement the algorithm. Okay, now let's see the code. In the setup, we have to import the libraries, the standard one, NumPy, Matplotlib, and sklearn, scikit-learn for the dataset, because in this code I used a synthetic dataset. We have to construct it because this is only a code to learn the algorithm and not a real study case. So the synthetic 3D dataset generation, to make this I use the command in scikit-learn make blobs. We have to choose 600 total points, 3 dimension, 4 is the number of clusters, so 4 labels, and the clusters STD is the variation of the dataset, the dispersion, the standard deviation of the dataset. If we choose, for example, a standard variation as 1.2, we will see that the accuracy will be 100%. If we choose a standard deviation as like this, we won't have an accuracy of 100%. Okay, import the libraries. Now we have create the dataset, the visualization. Okay, so 4 clusters in 3D dimension. 3 dimension. We have to split in train and test like this, and I have to normalize with standard scaler the dataset because this algorithm requires it. In this part I will show the code from the scratch part because we have to see the implementation from the baseline, and so we have to define the class capen and manual. I initialize the algorithm with k equal to 5, x train and y train, define the Euclidean distance, the prediction of the point, and the score. And the accuracy is 100%. Now let's see the code imported from scikit-learn, and the accuracy is 100%. Optimal case selection with cross-validation. We see that the optimal is like 11. The confusion matrix, a perfect confusion matrix, and the visualization of the prediction with non-incorrect prediction. The uniform distance versus distance weights, because we can also see the points with importance related to their distances, because if a point is near the testing one, so the one I want to predict, the label, I can assign to it a more importance, so a distance with more powerful. Instead, versus the case, the point near of my testing point is far away. And the final summary. Okay, now let's change the standard deviation of the dataset to see the difference. Let's try 2.5. We see that the points are mixed in this case, and so the algorithm won't work well. Let's divide in train and test case. The manual algorithm, let's say that, has an accuracy of 85%. In this case, the optimal case selection is equal to 20. The confusion matrix isn't perfect, but good, and in this case is equal to, with k equal to 20, 88%. The 3D visualization allows me to see the incorrect points, the incorrect predicted points, uniform and distance weights, and finally results, finally summary. Okay, this is the kappa nearest neighbor algorithm.